Hi, good evening, everyone. Am I audible?
Yes, ma'am.
Okay. So, week 8 has been completed. So, from today, we will start week 9. Today is the concept summary session for week 9. So, we'll go through all of the topics that are covered and we'll also see all the codes, right? So, let me share my screen. Is it visible?
Yes, ma'am.
Okay, just a second. Yeah. Okay. So, week 9 is about recursion. Right. So, anyone has any idea what is recursion? Anything you know about recursion?
Simply, ma'am, calling itself.
So recursion means basically a function calling itself, right? So what is the difference between iteration and recursion?
We call the function repeatedly, and in case of iteration, we just repeat a task. We repeat a
Right. So
task
in
in
case of
the interest.
iteration, yes, continue.
Yeah, so we basically repeat a task in iteration, but in recursion, we repeat a program, a function repeatedly.
So in case of iteration, what happens is we have this block of code, right? For instance, if I take a for loop, so the block of code that comes under the for loop, as long as the condition is being satisfied, that block of code will repeatedly execute. In case of recursion also, now when it comes to recursion, we have a definite function that is defined. That function will be calling itself again and again until what? So like in case of recursion also, in case of for loops or while loops, we have some condition, right? That until that condition is satisfied, you can keep on repeating the block of code, but as soon as that condition is violated, we'll stop and step out of the loop. So in case of recursion, that condition is known as a base condition. Okay. So same thing is happening. The idea is same only as iteration. So you are going to repeat the same function again and again until the base criteria is violated. So I have a very simple example here. So everyone I think knows about this. So there are these dolls called Russian nesting dolls, right? So these dolls are like what? So there is a big doll, inside that there is a smaller one, inside that there is a smaller one, and then there is a smallest doll which cannot be opened. So that outer doll can be thought of as your main function. Okay, that is the first time you are entering the function. And then when you call that function again inside itself, so it is the doll that is present inside the outer doll. So like this, you will go on calling the function until you reach the smallest doll, which cannot be opened anymore. So that means here my base case is finally being violated at some point, and then I'll start backtracking, right? So this is what recursion is. So just a function that calls itself till the base criteria is met. So there are some easier example that we can first see. So first, before we go into any code, let me give a few examples. So like we all know the most basic example will be summation, right? So if I want to have like a function called sum, let's say. So this sum function, it is supposed to find the summation of any number, like let's say first 10 natural numbers or first 20 natural numbers, like this. Okay. So if I write sum of 10, so this should give me the sum of 1 plus 2 plus 3 plus 4 like this till 10. Right. So when I write sum of 10, so this basically does this 1 plus 2 plus 3 till 10. So yeah.
Are you referring to user defined function? This sum takes your list, no? List or iterable.
I cannot hear you. Can you speak a little louder?
Just
Hello. Am I audible?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Please continue, ma'am.
Okay. So let's say that I want to find the sum of 10 numbers. Okay. So 1 up to 10. So instead of writing this, I can also write that I have this number 10 and I want to find the sum of the rest of the 9 numbers. This is exactly equal to this, right? That means everything before 10, I am outsourcing this task. So at a time, I'm only finding the sum of one particular number. So I'm saying that when I take sum of 10 numbers, it means 10 plus the other 9 numbers that come before it. So when I write sum of 9, this can also be written like this: 9 plus sum of 8. So sum of first 8 natural numbers plus 9 is what? Sum of first 9 natural numbers. So like this, I can continue till I reach 1, right? So every time that I am outsourcing this part, that means I am leaving this to do this later. So whenever I write something like this, so if this is the function name sum10, so it is calling itself inside the function. Then again, when it enters this sum of 9, this function call, then it will again call it as sum of 8. Like this, it will go on until we find sum of 1, which is the base case. Okay, so this is one example of recursion. One more example. So like this, can I write it like this? Sum of n.
So, ma'am, when you say n, then it will become n minus 1 will be sent as a parameter, right? That's what
Right.
Okay.
So if I write the recurrence relation, I can write sum of n is equal to sum of n minus 1 plus n. Right. This is the generalized relation. So this is the example for summation. One more example we can take, let's say the most famous one is factorial, right? So we all know 5 factorial means what? 5 into 4 into 3 into 2 into 1, right? So instead of writing this, I can also write that 5 factorial means 5 into, if I have a function, let's say fact n, so this takes some number n and finds the factorial. So for 5 factorial, I can also write 5 into factorial of 4. Factorial of 4 means this part, right? And when I go to the function call of factorial 4, I can say 4 into factorial of 3, right? So like this, I can go until factorial of 1, which is 1, and then I can again backtrack. This is one more example. Another one that is actually used more in real life, let's say compound interest. No
ma'am,
need to worry about.
you haven't mentioned the base condition for some.
Yeah, no, I haven't written the procedure or anything. I'm just trying to make you understand what is recursion. Okay, I'll go into the exact syntax and everything later on. These are just examples. Don't worry about base condition right now. So compound interest is what means if I have some principal amount and I have a rate of interest at which I am compounding it. So in case of compound interest, what happens? Let's say I have a principal amount P and some rate of interest R. So at the end of first year, this principal amount will be incremented by this percentage. Okay. So let's say I have 1000 as my principal amount. I'm incrementing it by 10%. So at the end of first year, I should get how much? This into 1.1, right?
1100.
Right. So this is the multiplication factor.
Yeah.
Just 1 plus 1 by 100, 10 by 100. So at the end of second year, whatever I got at the end of first year, that is this amount, 1000 into 1.1, this entire thing will be again compounded, that is multiplied by 1.1. This is the amount I'll get at the end of second year.
Right.
Similarly, at the end of third year, take this whole thing and again multiply by 1.1. Right. So this is, okay, let me write this in a better way. So if I'm trying to calculate compound interest at a rate of 10%, let's say, my principal is, let's say, 2000 rupees. First year, I get 2000 into 1.1. Okay, that is 2200 rupees. At the end of second year, I'll get this 20, that's 2200. Okay, so instead of writing it, I'm just writing the whole thing. So 2000 into 1.1, this was my sum at the end of first year. At the end of second year, this whole thing will be multiplied by 1.1 again. So this will give me some 2420. Then at the end of third year, whatever you got, this 2420, that is this entire thing again multiply by 1.1. So like this, if I continue, right, so at the end of, let's say, my year, if it is for n years I'm calculating, so I can write fn will be whatever was the money that I got at the end of year n minus 1 into the same rate of interest 1.1. Is this clear? Let's say n is 5, so it is a 5-year scheme. So how much money will I get at the end of 5 years? Whatever money I got at the end of 4 years into the same rate of interest 10%. Okay. I hope up to this everything is clear. So these are a few examples of what recursion is. Okay. Now we'll try to implement this in code. I'll stop sharing this. Any question up till now? Or is it clear for everyone?
Can you once more repeat me? Compound interest at
Yeah. See, compound interest, what happens? The entire amount is compounded over years. Okay, that means if I started with a principal amount 2000 and I'm applying compound interest at a rate of 10% on it every year, so at the end of first year I'll get how much money? 2000 into this 10, this 1.1 is coming from this 1 plus 10 by 100, this. Okay, so this rate of interest I'm just multiplying with it and I'm getting 2200 as the total amount at the end of first year. Then at the end of second year, how much money will I get? Whatever was my sum at the end of first year, you can count that as the principal for the second year. Okay, so this amount into 1.1. Similarly, for the third year, whatever amount I got at the end of second year into 1.1. So like this, if I am doing it for n years, so at the end of nth year, that is this one, how much money should I have? Whatever amount I had at the end of n minus 1th year into 1.1. Right, if n is 5, so at the end of 5 years, I should get how much money? The money that I had at the end of fourth year into 1.1. Understood?
yes, ma'am, understood.
So these are some easy examples. Now let's try writing the code for it. Okay, can you see the spider terminal?
Yes, ma'am.
So first, let's write it in the naive approach. Okay. So our job is, let's start with the first thing that we saw, that if I want to find sum of n numbers. Okay. So let's write a function for that. Let's call it sum. So if I put any n, it will find the sum of the first n numbers. So if I put 5, it is 1 plus 2 plus 3 plus 4 plus 5. So sum of n, now the function definition, let's write it. Let's have a variable called answer in which I will store the sum. So let's initialize it to 0. Okay. Then I have to just iterate to this range. So I in range.
Ma'am?
Yeah.
Ma'am, can you please increase the font size?
Is this okay?
Okay, yes.
So the range is n. Now answer, inside answer I'll store answer plus I plus 1, right? So that it starts from 1. Then at the end, so after every iteration, it will update answer like this, and at the end of the loop, I will just return it. So simply return answer. Right, this is the simple code to find summation of first n numbers. So let's call this, if I write print sum of 10. So sum of first n numbers is how much? 55. Right, let's see if it's working. Yeah, so I got 55. That means this code is fine. Now, what if I want to write it using recursion, right? So what will I change? Let's keep this same thing. The definition I will just change. The name will be still sum. Okay. So first I need a base case. Now I'll come to the base case. So what is my base case? If n is 1, then do I need to perform any summation? I can just directly return 1, right? So that's my base case. So until I get to 1, I have to keep on adding. So first condition that I'll introduce is if n is equal to 1. In that case, simply return 1. Okay. But if n is not 1, then in your else part you will write return. So what is the recurrence formula? N plus sum of, what will be in the bracket? N minus 1. Right. So this function should work exactly the same as the previous one. Let's try running this also. It should also give 55. Yes. So this is how you implement recursion, right? This is your first if is your base case, that until you reach 1. So how this will work, if I call it for 5, right? If I call this for 5. So what it is doing, first it is starting with 5. Okay. Sum of 5 it is starting. Now first condition it is checking, is 5 equal to 1? No. So I'll go to the else part. I'll return what? N plus sum of 4. Now the control shifts to this, sum of 4. Then again check the same thing. Is 4 equal to 1? No. Again come to else part. So 4 plus sum of 3. Like this 3 plus sum of 2, 2 plus sum of 1. So as soon as you come to sum of 1, then when you check this if condition, so is 1 equal to 1? Yes. So you return this one and it goes to the last function call. What was the last function call? 2 plus sum of 1. So this sum of 1 part returned 1. So it becomes 2 plus 1. That is 3. Now this 3 value is returned to the previous function call, which was 3 plus sum of 2. So now it is 3 plus 3, 6. Like this, it will keep on returning until we reach the first function call. Is this clear or should I write it?
Clear, ma'am.
Everyone, right? Okay. So this is implementing sum by your recursion. Now let's write another procedure for your compound interest. Let's try. So I'll write def, let's call it com. Two things I have to take as parameter. One is P is your principal amount. N is what? Number of years. Right. So I'm just taking, you can also take R, that is the rate of interest, but I'm taking the rate of interest as 10 here, so I'm not taking it as an argument. Okay. So if, first what is the base condition for this? When will we stop calling the function? When will we stop calling? When we reach the last year, right?
Last year.
So first I'll check if n is equal to 1. That means if you are compounding for just 1 year, then you can just return simply the value calculated in the return statement. Just write return p star 1.1. Okay, that is if your n is 1, so you're compounding for just 1 year. But if you're compounding for more than 1 year, if your n is greater than 1, then in the else part, we'll write the recursion. So then I'll return what? Compound? You tell me. P, comma, n minus 1, right? And this whole thing should be multiplied by 1.1. So at this point, when let's say n is my p is 2000, like that example, n is 5. So first iteration is 5 equal to 1? No. Go to the else part. What will I compute now? I need the previous year's compound interest, right? So P4, for P4 I will compute. So control shifts here. Then in P4, you again check that n is 4. So 4 is not equal to 1. So you go to, again call this function with P comma 3. So like this, when you go for P comma 2, P comma 1, at that point, at the last call, P comma 1, so n is 1 then. Then you can directly return P into 1.1. So this is what? This is the compound interest after the first year. This you will backtrack to the second year, then the total amount from second year, you will backtrack to the third year, to the fourth year, to the fifth year, like this. This is the one for compound interest, right? Let's check once if it is running. So if I print, let's take 2000 for 2 years if I do. So this should print that sum that we saw, that 2420 should be the answer, right? It is giving the correct answer, 2420. This function, everyone, it is clear, compound interest? Anyone who did not understand? Okay. So we'll go to one more function then. Let's write the factorial one also. So previously we have written factorial function without recursion, right? So that you know. Now we'll try writing it using recursion. So let's call it fact. So I want to find factorial of any number n using recursion. So here for factorial, what do we know as the base case? 1 factorial is always 1. So that's our base case. If n is 1, then I'll simply return 1. Okay. So first line will be the base case. If n is equal to 1, then simply return 1. If n is not 1, now write the recursive statement, return. What should I write? This you should be able to say now.
N minus n
into factorial of n minus
n into n minus 1.
So factorial of n minus 1.
Factor n minus 1, correct.
Then outside I'll write star of n. So that when it backtracks,
Yeah,
I'll be factorial 4 into 5. Yes, like that. Okay.
So in the recursion function, always the first condition should be the base condition.
The base case, yes.
And the else part should always have the
recursive call. Okay. Because first we need to check the base condition. If we reach base condition, no need for more recursive calls.
Okay.
Okay. So let's try running this also. If I write,
without else also it will work.
Yeah, you can write it without else also. So if I write print fact of 5, this should give factorial 5, 120. Okay, so these are very simple recursive functions. Now why we are writing recursion, these functions, why we need? Okay, because the main thing that we are trying to build up to in this week is binary search. Okay, so there are two different, I will get to that, but let me give you a brief introduction. So we have two different kinds of searches that we mainly use. One is linear search, one is binary search. Okay, so linear search, what it does is, let's say we have a list of elements. Okay, and we are looking for a certain element in that. So linear search will linearly check the entire list from the first element to the last element. So if I have n items in my list, okay, are you familiar with timing complexities? Like how much time a program takes to run?
Not yet, ma'am.
No.
Yes, yes.
Okay, no issue. See, if I say that I have n elements in a list, okay, Now I want to check a single element, whether it is present in that list or not. Okay. Now, if that element is, can others please mute? Who is this person?
I think it's Sony Tapti. Could you please
I'm not able to mute people.
your Sony Tapti?
Sakshi, can you please mute yourself? Yeah, okay. So yeah, like I was saying, if I have a list of n elements, okay, and I'm trying to see that if a certain element, let's call it x, if it is present in that list or not. Now, since I am using linear search, so in linear search the procedure is simple. I'll go from the first element, second element. Every time I'm taking an element out of the list and matching it with my x, that whether it is equal to x. If so, if I find such element which is equal to x, I'll be able to say that yes, x is present in this list. But in the worst case, what happens if x is such an element which is not there in the list? In that case, if list has n item, you are going through how many elements? N elements. You are checking for every n element. So in that case, the time complexity, that is how much time this program takes to run, becomes order of n. Okay, so this you will learn later on when you learn algorithms and everything. So linear search has a bad time complexity. That is, it takes more time to search for an element in a list. So the worst case becomes order of n. And if you find it on the first go, that is the first element is the element you are looking for, then it becomes order of 1. Okay. But anyways, we will think of the worst case complexity. Now, how can we make this better? How can we make it a better search? That we don't have to go through all the elements in the list. That's our goal. So that's where binary search comes in. Okay. So binary search is the main procedure that we are going to learn in week 9. I'll just give you a brief of what it's like. So if I have a list of, let's say, n elements, binary search, what it does is, if you give it some element x and say that, okay, check if this is present in my list or not. Okay. So instead of linear search, instead of going through the entire list, binary search will first find the middle element of the list. Okay. It will first find what is the middle element. Then it will compare that middle element with the element that you are searching for. If it matches, very good. If it doesn't match, then we check two things. Okay, so binary search works on sorted lists.
Ma'am, you are sharing the program screen, not your.
Yeah. I'm just saying, okay, I'm not writing
Okay.
anything.
Okay, fine.
So binary search works on sorted lists. Okay, so it will first find the middle element of the list and check that whether the element you're looking for is the middle element or not. If it is, then very well. If not, then we have two other options. Since it's a sorted list, that means if my middle element is less than the element that I'm looking for, that means my element that I'm looking for lies in the second half of the list, right? From the middle element to the end of the list, since it is sorted. And if the element I'm looking for, my x, is less than the middle element, that means it lies in the first half of the list. In any case, what binary search does is, every time in every iteration, okay, it breaks the list into half. So first you find the middle element, that splits the list into two. Then again you keep on doing this. So once you divide the list into two, now you know that on which part of the list your element you are searching for is supposed to lie, whether it is less than the mid element or greater than the mid element. So you will search in only that part of the list. Again, you will split that part of the list by a middle element into two more lists. So every iteration, the list will keep on breaking into halves. So in binary
This
search,
this is
yeah,
applicable for only numbers, ma'am, or it's can be used for any other type of data type like
it
string or
can be
anything.
used for sorted lists. Okay.
Okay.
So what happens, since we are breaking down the list every time, so we are never going through all the elements in the list. So the time complexity recovers a lot better than linear search. So the basic time complexity for binary search is order of log n. Okay. No need to memorize any of this, just telling you. You can check it using that time method in the time library, right? So you can check that how much time linear search and binary search take. Now, one interesting fact about binary search is that I can issue binary search on a sorted list. Now, have you heard of linked lists? Anyone has heard of linked list?
No,
Yes,
ma'am.
ma'am. It's mainly about
Yes, ma'am.
list. Like it consists of elements which is divided into two subparts. One is
Right.
data, and another is a pointer or an address which
Hmm.
links with the next.
So
Uh,
Base
for
load.
those, see, for those who don't know, I'll just quickly write it once and tell you, because this is a very good interview question. Okay, I've seen this many times. So since we have the opportunity, let's just discuss it once. See, a linked list looks somewhat like this. Okay, so it is nothing but the elements in it is a storage container only. Okay, like stack, queue, these are all storage containers to store data. So in a linked list, every element looks like this. So there is an part where you actually have the data. This is the data part, and every node will have a link part. Okay, so this is the data part. This will contain your actual element. This part will link part contains what? This is a node. Okay, link part contains the address to the next element or the next node. So it will point you to the next node in the linked list, which again has the same structure, data and link. So like this linked list continues until you reach the last node. So for the last node, there is a data part, but the link part is null because it doesn't point to anything. But in linked list, so the question that I'm talking about is they ask in interviews that can we apply binary search to linked list? So the answer is no. Now why it is so?
Cannot,
Because
it
in
cannot be
case of,
sorted out, no?
because the
the
links
thing
will
is
be
that,
then disrupted.
yeah, because linked list is not stored in consecutive locations. Okay, the nodes can be stored anywhere in memory, and it is not possible to find the middle element. So
Yeah, but
unless you
because
find the middle element, what
yes,
we do
like
is we
we have.
find the index of the first element, index of the last element, add them, divide by 2, that is our middle element. But in case of linked list, the index can be anything of the first and the last element. They're not related because they're not stored in consecutive memory locations. Okay, they are stored anywhere in the memory. So it is not possible to find the middle element. And if you can't find the middle element, binary search is not possible.
Now,
Okay.
can we sort them? Can we not sort them?
Sort you can do, but how will you find the middle element?
Like we could do something. I don't know. Like we can ignore the links. Like it's just a link, and we can ignore it, and we can look onto the data since it's a sorted list. If it's an unsorted list, then sorting it might be a challenge.
Yeah, but if you don't have the link, you don't know what is the next node. So if you don't have the next node, how will you know that it is sorted or not? Even if a linked list is sorted, okay, you how will you apply this binary search algorithm on it? Finding the middle element, that is the key here. Okay, so this is one thing that binary search cannot be applied in linked list like this if it's not sorted. Okay. But yeah, anyway, this is not in the scope. I'm just telling you this. Let's start writing the code. So first, what we will start with, let's do a simple algorithm first. Let's say if I have a list, okay, and I want to check if 0 is present in the list or not. Okay, so let's call the function check 0. Okay, I'll write it here only. The screen is visible, right?
Yes, sir.
Yeah, ma'am.
So let me say I have a list like this: 11, 12, 16, 2, 3, 4, 0, 5, 6. If this is my list, I'm trying to find out if 0 is present in the list or not. Okay. So there can be two things. I can write a definition of a function called check 0, which will take this list as an argument. And what it will tell me is if it will give a true value if 0 is present in the list, it will give false if it is not present. Okay.
Please
Simple.
increase your
Yeah.
size. Thanks, ma'am.
So if I just write in English, I'm not writing the code. If I just write this check 0. Okay, it is taking a list as parameter. So the first thing it will do is check the first element. Okay, and the rest of the list you will just outsource. Just like in case of summation, what did we do? Sum 10. So first take out 10 and then sum of 9. That is the outsourced part. But we will do this later on in the next call. So outsource the rest of the list. Okay. Now, if I want to write this in a bit more organized manner, I can say check 0 takes a list as argument. We will first check if L of 0, that is the first element, if it is equal to 0 or not. Okay, if it is 0, return true. Else, what should the else part contain? So now I have the rest of the list to check. In case the first element is not 0, I have to check through the rest of the list. So I can simply write check 0.
n-1.
So from 1 I start to n1. So from the second element to the rest of the list, right? But there is one more thing that we are forgetting, that what if the list is empty? So for that also we have to write a condition if length of L is equal to 0. In that case, you will simply return false. So an empty list doesn't contain anything. So just return false.
Acha, ma'am, I have a question.
Hmm.
As far as I understood this algorithm, it means that if the first element is not showing 0, then we just like delete that portion and then we look at the rest of the list.
Hmm.
But I can see that according what you've written, that check OL from 1 to n-1, it indicates that uh, like we are sort of deleting the first as well as the last element.
No, this will go till length of L minus 1, right? So this is length of L minus 1 is what? If I have 7 elements, so the loop when I run it, it starts from 0th index, right?
Yes.
So n is 7, so it should go up to 6. So
But
that's why the first from 0. Okay,
but instead of that, can we do something like we can just set that check OL 1 2 and we just skip the, like, we just don't give a ending point, because it means that the index ends in n-2.
No, it will check till the last. So if you want,
No,
you
I
can
mean
change
that,
this if you. Okay, this one you're talking about, right? That
yes,
this
I'm
will
talking
give.
about the recursive part.
So
Like
this you're saying this is okay.
no, I'm
If
just,
I just
if
if I
you
just
just
write length of L, okay, instead of this n, okay, let me remove this. If I remove this and just write length of L here, that will be okay.
yes,
That will check from second element to last.
yes, that is what I was talking about. So I was kind of confused, like this this message that I just written there, this syntax, because
Yes.
what I saw in the video as well as now, that it seems like as if the first element as well as the last element has been deleted.
No, it will go from the second element to the last of the list. Okay, only the first element is taken out. Yes, it is better to write. You just write length of L because n can be confusing. Why I put n? Because in my mind I am thinking that n is equal to the last of the list plus 1.
Yeah.
Okay. But it is better you write length of L. This is clearer.
Yes, that is what I was thinking. Like, so somehow I was thinking that they were like deleting the last element, but
No,
it's okay.
just the first one. Okay, every recursion, every recursive call, we check if the first element is 0. If it is not 0, then you remove that first element, check the rest of the list. So wherever you are in the list, you just go till length of L. Okay, so since we are removing the elements, so every time you are going to start from the first index to the last, right? That is the 0th index is now gone. So we are starting from first to last. So three things we have to check. First, we will check that whether length of the list itself is 0. So this condition is better if we write it in the first only, if list is empty. In that case, you can directly return false, nothing else to check. If not, then you check this condition, whether first element is 0. Directly, if you find it, very good, return true. If not, then you have to keep on checking. So here is the recursive call. Okay, now if we write this program, okay, I'll just delete this list, not needed right now.
Excuse me, ma'am.
Yeah.
Ma'am, please explain the second line.
The else part.
Yes,
This one.
ma'am.
See,
Ma'am, can
No,
you
ma'am.
explain whole code?
the whole code, right?
Yes, ma'am.
Yes, ma'am.
See, if I have a list of, let's say, 10 elements or any number of elements, I'm trying to check if the element 0 is present in it or not. Okay, so the first condition I will check
Ma'am,
is
I'm
this
unable
one. Yeah.
Ma'am, I'm unable to understand if L contains 0 equals to 0. This much.
This is index, right? This third bracket is index of a list. L of 0 means first element in the list, L.
First element.
Yeah.
Okay, ma'am.
First
Thank you.
condition we will check is this line. Okay. So we will check that whether our list has any elements or not. If the list itself is empty, then there is no possibility of 0 being present in it. So
Yes,
I'll directly return
false.
false. Second if condition will be this. We are checking if the first element in the list is 0. If we find it, then you return true. If we don't find it, then we still have to go through the rest of the list. Right. And now since I know that in the 0th index, 0 is not present, so I'll start from the first index. So 1 till the length of the list, that is end of list. Okay. Now
Okay, ma'am.
once I call this, it will again go to this first line. Check if that after removing the first element, did my length of list become 0? If not, if there are more elements present, then you check this line again. Is the first element 0? If not, then you again come to the else part. Now you will start from the next index to the end of list. So this line is the recursive call. Okay, if I write the code, it will become more clear. So let's call this check 0. Okay, and I'll take the list L as parameter. So first, okay, let me write some comments also. So if the list is empty, then return false. Okay, so the first line of code should be what? If length of L is equal to 0, then return false directly. Or let's write 0, return 0. We are going 0 and 1. Okay, so 0 is false. Next, what we will check? First element. So L of 0 is equal to 0 or not. If it is 0, then we will return 1. That means 0 is present in the list. If it is not 0, now we have to write the else part. The else will contain return check 0. What should be in the parenthesis? What is the parameter I will pass for the recursive call?
The rest of the list, which is L.
L of
Bracket
index
open.
will go from
L of 1.
1 to length of L.
1 to
1
length.
to length of L. Correct. Okay. So this is the simple procedure. Now let's call this, check if it works. Let's write print check 0. I'm just directly giving the parameter here. Okay, so let's write a list 1, 2, 3, 0, 4, 5. So this should return 1, correct? Let's see. So it is giving 1. Now if I remove this 0, it will simply give 0. Okay, so this is the check 0. So why I'm starting with this? This is just the first part before we actually go to the linear search. First we will do linear search, then we will do binary search. Okay, so check 0, this definition is clear for everyone?
Yes, ma'am.
Ma'am,
Okay. Yeah.
uh, um, Can you just how to check the time it takes
Yeah, I'll
execution
show you
time?
the time. So you just have to import time, and then there is some. Okay, let me see here if I write. So the way that we can check that how much time something is taking, right? That how much time it is taking to run a procedure. So what we can do is first take a variable, let's call it a. Inside this, I will call time dot time. Okay. So this method does what? This time method, it calculates time from some predetermined epoch. Okay, it's called an epoch. That means a lot of, like, it's a lot of time before present. Okay, so it is calculating time till present from some standardized time in the past. Okay, so if I first calculate that what is the time right now at the present, I am keeping that time at a, then I'm running this procedure check 0. Then if I have one more variable in which I again call this time method, so now some time has lapsed while that procedure ran, right? After this, if I write print b minus a, so this should give me how much time it actually took, and let's check if it is working. Yeah, so this actually didn't take any time. I mean, it's a very small time. That's why it's not showing here. But when we do your linear search and binary search, then you can see the difference in time and how much time has lapsed. Okay. Better also if it is not visible here in Spider. I don't know. I have had this problem before also. If it is not visible here, you can check out the lecture for binary search. Okay, so there sir has showed you that how much time it is actually taking. It's not necessary, just to show you that binary search is a better algorithm than linear search. But yeah, this is the way. So you have to import time and then just take the time before running the procedure and after running the procedure, and then get the difference of two. That is how much time it took to run the procedure. Okay, anyways, this will take very less time.
Would it take any argument?
Sorry.
Won't it take any argument?
No, just call this method. Just call dot time. Okay. No argument required here. Okay. So now, since you are familiar with searching, how it goes, so now let's come to sorting. Okay.
Ma'am,
Yeah.
uh, once we have so many sorting built-in functions like sorted and dot sort, why do we
Mhm.
need sorting
Because that
like
is in Python only, right? In other programming languages, you have to write the sort function yourself. If you are using Java or C, in anyways, in Python you have
okay.
dot sort, but you need to know how that sort function, the inbuilt function, what its logic is, right? Python is, that's why it is a very easy language to code in. If you started with C, then you would have to learn sorting first thing, sorting, searching, all this. There are no inbuilt library functions, anything. Okay, so the basic idea of sorting is what? Let's say I have a list. Okay, it has these elements 3, 1, 5, 7, 2. This list, I want to sort this list. So easiest way to do it, if I want to do it in ascending order, by default we say, whenever we say sort a list, by default we mean ascending order. Okay. So what is the first thing I should do? I should find out what is the minimum element in this list, right? So this is the minimum element. I will take this element out. So what elements are left in the list now? 3, 5, 7, 2. 1 is out. Let me put 1 in a separate list. Then among these 4 elements, you again find which is the minimum one, 2. Take 2 out, append it to the list that 1 was in. So it becomes 1 comma 2. Third time when you go through it, again take minimum element. So like this, when you take the minimum element out every time, you will be left with a list that contains only one element. So you can just take that element, append it to the new list. So this is how basic sorting works. Okay, so you can just find the minimum element, put it in a new list. Now we can just try to write the pseudocode, right? So if I
Ma'am,
say that, yeah,
Is this selection sort?
Is the
Is this selection sort? Am I audible?
yeah, you're audible.
Is this selection sort that you're explaining?
No, the code I will write later on. I'm just trying to give you the concept of sorting. Okay.
No, ma'am, I'm asking, is this selection sorting?
Yes, yes. So basically, there are three different types of basic sorting: insertion, selection, bubble sort. Right. So yes, this is one of those. And there are also actually there are many types of sorting. There is also quick sort, merge sort, all of these different radix sort. But these are much more complicated codes. For right now, we'll just call this sorting. Okay, I'm not naming what type of sort it is. Just call it sorting for now. Okay. So in this one, what happens? First thing we have to do when we write the code is we need two different definitions. Okay. So one function, let's call it f1. This function will be what? To find the minimum. Find minimum element. So how many times we have to find minimum element?
N minus 1 or length minus
Until the list becomes empty, right?
empty or the
Or
last
list
last one.
contains only one element. Okay. This is the base condition. So until that condition is met, we will keep on calling this mini function. Okay, that will find out the minimum element. And there will be one more function, which is the actual sorting function. Okay, now let me write the code, and as I write, I'll explain the lines. So first, let's write the code for minimum. This so everyone should be able to write by now. How to find the minimum element in a list. So anyone can tell me what is the logic to find minimum element?
We can use the min function.
I'm not using any inbuilt functions or anything. Okay, I'm writing the whole code. So how will if a list is given to you, how can you find the minimum element? We discussed it in CT also.
Yes, ma'am. We have to initialize minimum to the largest first.
Okay, if I don't know what elements the list contains, in that case, what will you
We can
initialize?
take is infinity, ma'am. Float of I and f.
Can I not take the first element as minimum? Can I not assume that the first element is minimum, and then I will keep on comparing the rest of the elements with that element? If I find an element which is smaller, I'll just update my minimum, right? So let's say
Yes, ma'am.
mini is a variable which contains the first element in list L0. Okay, now I'll run a for loop. So for x in L, for every element, we will check what? If x is less than mini. If so, then we will just simply update mini with x, that we found a smaller element, right? And then once this procedure is done, once the for loop is over, definitely mini will be containing the smallest element in the list L. So I'll just return that, return mini. Is wait, let me increase. Is this clear to everyone? How to find the minimum?
Yes, ma'am.
Okay, so this
Yes.
is just the minimum procedure that we'll have to call. Okay. Now, what is the main procedure, that is sorting? Let's write that. So let's call it def sort. It will also take this list L as argument. Okay. Now the recursion actually will happen inside the sort procedure. So this sort procedure will be called again and again. Now since we are using mini inside the sort procedure, this will also be repeated every time we go for a new recursive call. Okay. So the idea of this procedure is to recursively sort list L. Okay, so the first thing we will check is whether our list is empty or it contains just one element. If list is empty, that means we can just return the empty list, nothing to sort. If list contains one element, then also nothing to sort. So in both those cases, you just return the list as it is. Right, so the first if statement will be the base case, that is if L is equal to empty list. 1, another is or length of L is equal to 1. If any of these cases is true, simply return L. Done. This is base case is done. Now, what happens if it is not any of these cases? So next we will have one variable, let's call it M. Inside we will store the minimum. So call mini function with list L as parameter. So this will store the minimum from list L. Now, okay, I should write comments so that when I share it, you will understand. So M now contains the minimum element in L. Next, what I'll do, once I found the minimum, what was I doing in the PDF? See, when I wrote this, what was the next step? You have to remove the minimum from the current list, right? So next step, I will just do L dot remove M. So remove M from L. Next, return. So this is the recursive part. So what should be the return statement? Look at this where I wrote. So what was I doing? Minimum element I'm removing, putting it in a new list, and then what was I doing? Again calling the same sort function on the rest of the list. Right. So if I want to write that in the return statement, what should it be? Return what? First put M in a list. Okay. With this we will append what? Again call sort of the new L. Is this okay? So I'll just write the comment here also. So we remove the current minimum. Okay. Next, this line, what we are doing? We recursively sort the smaller list L now, because L is now a smaller list than the original list, right? Since we removed one element.
What happens if we have duplicate values?
In sorting, so usually we work with distinct elements only. But if you sort elements, then duplicates will come in a row, right? So you have to keep on removing them, the duplicates one by one. But usually sorting is done on distinct elements only. Okay, or you can transform it into a set first, so that will get rid of the duplicates.
I mean, in this case, ma'am, duplicate will be there in sorting order.
Yeah, if you sort this using a list with a list that contains duplicates, so they will be there. Okay, since this is a list, so it can have duplicates, right? It's not a set. So they will be there present. Yeah. Okay, so up to this is the recursive call. So when I do this recursive call, what happens? The smaller list now again comes here. Again you check whether the list became empty or it has one element. If none of those cases, you again go call the mini function, find the minimum of the list. Again remove that minimum, append it to this list, right? Every time we backtrack, the elements will keep on getting appended to this list where I put the minimum element. So if I want to run this procedure once, check if it works. Let's take a list. 5, 6, 71, 23, 19, 1, 7. Okay, this is my list. Now if I write print sort of L, let's see if it gets sorted. Yeah, it is sorting the list in ascending order. Okay. Similarly, you can do in descending order also. So that in that case, you just have to find the maximum first and then remove the maximum element like that. Okay, let me just try for a duplicate also. What happens? So if I add one more 5 here. Yeah, see there are just 2 5s. Okay, list will not remove duplicates. So is this procedure clear for everyone? Basic sorting?
Doubt,
Yeah.
this last problem, we are writing M of plus sort of L. Can we write sort plus M?
M plus sort of L means what? When you go for the next call, this sort of L will find the next minimum, right? And again, when you backtrack, that is when you come back to this procedure, so this becomes, let's say the first, okay, in this list, what is the first minimum? Forget about the duplicate. What is the first minimum I'll find? 1, right? So initially this list contains just 1, the new list. Then you call sort of L again. So when you call this function, now what is the next minimum? 5.
Yes, ma'am. 5.
Okay. So it will be what? Now 5 plus again sort of L, where 5 and 1 are both removed now. So like this, you keep on appending to this list only. Okay, all the minimums will be appended to the same list, but as you are backtracking, so they will be in the proper order, ascending order. Okay,
Yes,
so the
ma'am.
first, yeah. Is it clear, everyone? See, if this is not clear, then I cannot go to linear or binary search. Okay. So first you tell me, is this clear, everybody?
Yes,
Yes, ma'am.
ma'am.
Okay. So now the next thing we'll do before I go on to binary search, let's just take a small example to understand it better. Okay. Let's say I have a dictionary. Okay. If I have a dictionary, what is the procedure of finding any word in a dictionary? Okay. Let's say I want to find the word rainbow. Let's say this dictionary has 1,000 pages. Okay. So I will start, if I am using binary search to search this word, what will happen? First, I'll find the mid element. So what is the middle page? 500 page. Okay. Now I will directly open the 500th page. If in that page I see that the first word on that page is starting with, let's say, P. So by looking at this, you can say what? That rainbow is present on the first half of the dictionary, that is between 0 to 500, or in the second half, that is 501 to 1000. Which one is zero? This rainbow present? Second half. This half, right? Now once I go to this second half, again I'll find the mid. Let's say the mid is 750. Page 750. On page 750, I see that there is something word that starts with S. So now I have again two choices. So is my word rainbow going to be from 501 to 750 or from 751 to 1000? Which half? First half. So like this, see how much my time is being saved. So every time I'm going for the next recursive call, the sample space is being divided into half. So first I had 1,000 pages, then I'm only dealing with 500 pages, then I'm only dealing with 250 pages, next I'll deal with 125 pages. So like this, by a few recursive calls only, you will reach your actual page that contains the word. Okay, so this is the idea of binary search. Every time you go for a recursive call, the sample space gets divided in half. Okay. Now, before we write the code for binary search, let's write a simple code for linear searching first. So linear search, I told you, nothing special, just you have a list. There is an element X I'm trying to find in the list. So what I'll do is I will check from the first element till the last element in my current list and match every element with the desired element. If it is present, some match will give a true value and I will return true, that yes, this element is present in the list. If not, then it's just your bad luck, you have wasted order of n time and the element is not there. So it will just return 0. Okay, so let's call this procedure obvious sort. So this is what professor used, so I'm using this name. You can call it linear search also. So obvious search is my function. It's taking a list as an argument, and since it is searching, that means I'm searching for some element, so you have to also take the element as argument. Let's call it K. Okay. Now, for x in L, I have to go through every element in the list, right? So what I will check is if x is equal to k, that is the element that I'm looking for, then I will return 1. If after going through the entire list still I don't find the element, just return 0. This is that simple. This is linear search. Okay. So let's form a list. Let's call it L range. Let's take first 100 numbers. So what does our list look like? This, right? This is our list. 0 up to 99. Now what do I want to find? Let's say I want to find is 56 present in this list using obvious search. So you'll write print.
It's basically linear search, right?
Yeah, same linear search. I have just changed the function name. So you check L comma your number that you're looking for, 55. So this should return 1. Okay, this is returning 1. Here instead of 55, if I write -2, this is returning 0. -2 is not present. Okay. Now this first call that I did for 55, that will take a less time than searching for -2. Why? Because when I'm searching for 55, I'll go from 0 to 55, I'll find the element and I'll return 1. But when I'm searching for an element which is not in the list, that means I will go till the end of the list, till 99, and then I can say for sure that it is not present. Okay, so even if it is a very small fraction of time, this will still take more time if some element is not there in the list. Okay, now this is linear search. Now the improvement upon this is our binary search. So first we will do the basic code for binary search without any recursion. We'll just use a while loop. Then we will do it using recursion. Okay, so let's write it
Ma'am,
here only.
what is the difference between membership update and obvious search?
I can't hear you. Come again?
Am I audible?
Yes.
What is the difference between membership and obvious search?
Same thing. Membership checks what? That whether an element is a member of a list or not. Right.
Linearly.
So that member that you are checking, that function, what does it have in the backend? What is the code for that function? This is the code. It is checking whether it is present in the list or not. Right.
Okay.
So now can we write a piece of code that searches for a given element in a list L faster than this obvious search? That's the goal. Okay. So let's start writing for binary search. So this, please be a bit mindful. This is a bit bigger code. So binary search will take again 2 arguments, the list and the element you are looking to find. Okay. Now this function is an alternative. Okay, both of these work. Obvious search works, binary search also works. Now what is the difference is that exactly same output you will get, but it is the more efficient way. Binary search is more efficient way, takes less time. So later on when you study algorithms, then we will come to discuss the concept of timing complexities, that is order of n, order of log n. This is how much time a program takes to run. So we always want to optimize our code, that a code that will run faster, right? So this is the more efficient search. So what should the first thing be that we should check? So 2 things should be here. Okay, one is the beginning of the list and one is the end of the list. Why we need this? Because binary search searches using what? The middle element. So to find the middle element index, I need the first index and the last index, right? So let's write begin. This is the first index, which will always be 0. Next we'll write end. What should end be? Length of L minus 1. Okay, this is first index, last index. Now the while loop starts. So while end minus begin is greater than 1. So why is this the condition? Anyone can answer? why we keep on searching until n minus begin, that is these indices, the difference between them is always greater than 1. Only then we will keep on searching. Why is that?
When the queue comes to the end, when the end and begin become same.
That means end and begin, if they are greater than 1, the difference, that means there is more than one element between them, right?
More than one element, correct.
So there is still a point in searching. Now if the difference becomes 0, when does it, or if the difference becomes 1, let's say, that is, let's say begin is at 19, end is at 20. Okay, begin is at 19th index, end is at 20th index. So these are individual elements, begin and end. So then you can directly just check that whether begin is the element that you're looking for or end is the element that you're looking for. What if begin and end, the difference becomes 0? That means they're both at the same index, right? So why this is happening is because every time we call this or we iterate, since this is not a recursive way, this is the iterative way. So every time we iterate through the while loop, either the end or the begin will change. Okay, because we are changing the list every time we are going for one iteration, the list is getting divided into half, like we saw. So that means if the end was first length of L minus 1, that is the end of the list, after the first iteration, the end will become the middle of the list if I want to search in the first half, or the begin will become the middle of the list if I want to search in the second half. Okay, it will get more clear when I write the code. So this is the base condition, that when end minus beginning is greater than 1, that is there are more than one elements between end and beginning index. Okay, so we will handle the case when number of elements is less than or equal to 1. That also we will handle later on. So then we will find the mid index. The first thing we'll do in each iteration is find the mid index. Mid index is nothing but begin plus end by 2. Right. Now if the mid is indeed k, that is the element that we are looking for, then we will directly return true and stop the code. No need to go further. So just write if L of mid is equal to k, right, then directly return 1. If that is not the case, now the second case. Okay, let me write a comment here so this will make more sense. If mid is indeed k, then return 1 and stop the code. Okay, if it is not, then next case what we do, next we will check if mid is greater than k. In that case, cut the list in half. Which half? Or I can just write cut the list cut the right side and retain the left side. So why I wrote this, that if it is if middle element is greater than the k that I'm looking for, then I have to cut the right side of the list and retain the left side. Why? That means that if middle element is greater than the element I'm looking for, since this is a sorted list, that means my desired element definitely resides in the first half of the list, correct, from the beginning to the mid. So what will be the next code? If, just write this in the form of an if statement. If L of mid, three cases can happen, right? Either mid is the element you're looking for, or mid is greater than the element you're looking for, or mid is less than the element you're looking for. So in that way, you have to cut the list in two different halves if mid is not the desired element. So first case is that if middle element is greater than the element I'm looking for. In that case, do I need to change the begin index? Okay.
I think and
Look, I'll just take a small example here so don't have any confusion. See, if this is my list, okay, 1, 2, 3, 4, 5, 6, 7. Okay, this is index 0, this is index 6. So what is the middle index? 0 plus 6 by 2, 3. That is 1, 2, 3. This is my middle index. Let's say k is 2. I'm looking if 2 is present in this list or not. So begin is this 0, end is this. Middle is 4. So in this case, mid is greater than k, correct? 4 is greater than 2. So which part of the list will I find 2 in? In the first part or in the second part? First part. So do I need to, now I have to find the middle element in the first part of the list. So do I need to change my begin index or do I need to change my end index?
Begin index.
Why
Begin
will I
index,
change my begin index?
because the element
I
are
need,
present in begin index.
no, begin index is the first index of the list. Element is present in the first half of the list, right? So my end index is the end element. Now after the first iteration, after I found the mid, that is 4, I understood that 4 is greater than the element I'm looking for. Now since it is a sorted list, that means that my element is present in the first half of the list before 4. That means this list I have to now search in. So again I have to repeat the same procedure, right? Now I have to find the mid in this first half of the list. So begin index can remain 0, but end index should become what now?
Middle element.
Mid minus 1, that is this index. Mid was 3, mid minus 1 is index 2. Mid we have already checked, so just go to the element before mid in the left side of the list. 1 second, let's not call it B. This is end index. So now your begin is 0, end is 2. Now when I again do the sorting, what is the middle element in this? 0 plus 2 by 2, that is 1. So what is the middle element now? 2. So is mid equal to k? Yes. So you found it. Now if mid was, if k was, let's say, if I was looking for 6, in that case what would happen? The first iteration is fine, mid is 4. Now when I check that is mid less than k, this becomes true. So if mid is less than k, that means k is higher. So it will be in the second half of the list. So here which index will I now change? End remains 6.
Begin.
Begin will be what?
Element
Mid
plus
plus
one.
Mid,
1.
mid plus one. Mid plus
Mid
Mid,
one.
plus
mid
1.
plus 1.
So now I will check in this list. Again you check that, okay, mid element was, index was 3, so mid plus 1, this is index 4. So what is the middle element now? 4 plus 6 by 2. That is 5. So fifth index is this. So is the mid equal to what we are looking for? Yes. So you found the element. Okay, this
Ma'am,
is a very small list. Yeah.
ma'am, what if the length of list is even?
Then also, see, that's why we are taking this operator, right? The double slash. So it will not take the decimal part. So if the length of the list is even, right? If there are, let's say, 8 elements. So in that case, your begin plus end. Okay. Let's say there are 6 elements in the list. So what should be the middle? 6 by, if I do a direct, okay, let me write it. If I have a list like this, 1, 2, 3, 4, 5, 6, fine. This is index 0, this is index 5, correct? What is the middle element? 5 by 2. This becomes what? 2.5 something,
2.5.
right? But if I write 5, if I use this operator, then it will just give me 2, not take the decimal part. Okay. So in case of that is why we are using this operator, that if I have even list, then also I will find a midpoint. Okay, so this will be the midpoint. Now there are different ways of doing it. If you want to make sure that since there are these two can be the candidates for middle element. So if you want to take the second candidate, you can just divide and put a ceiling value that, okay, I'll take the ceil If it's 2.5, it will take the third element. It will take it as 3. But in my code, I have taken the first one only. Okay. So is binary search clear how it is working? Can we write the code now?
Yes.
So now you saw in the example that what happens if the mid becomes greater than the element we are looking for. Then what do we do? What is changed? End or beginning? Middle element is greater than the desired element. So desired element lives in the first half or the second half?
First half.
First half. That means what do I need to change? Begin or end?
And
So end will become what?
mid minus 1.
Mid minus 1. Correct. Next case is what? If both cases we have to write. If L of mid becomes less than K, then what is changed?
Begin.
Begin will be what?
Mid
Mid,
plus 1.
mid
Mid
plus
plus
1.
1.
Yes. So now see, this all is inside the while. Okay. That means this condition is prevailing that n minus beginning is greater than 1. Now there will come a point when this gets violated, right? This condition gets violated. First what will happen, that n minus begin will give equal to 1. So whenever this condition is violated, then what do we learn from that? That when this condition is violated, what can we say for sure? Okay, let me write it as a comment. So now this is outside the while loop. That means we are out of the loop now, since condition is not satisfying, condition is violated. So if we are here, it means that we have
Singleton say, singleton list.
no, it means that we have not found the
Only two
element.
elements.
We have gone through everything, but we have not found the element. Okay. Also, if we are here, it means that the while condition is violated. That's why we are out of the while loop, which means two things, right? End minus begin is less than or equal to 1. Is this okay with everyone? If we are out of the loop, that means end minus begin is definitely less than or equal to 1. Right, that's why the condition is violated. See, this condition is violated when n minus begin becomes less than equal to 1. So now what do we need to check? If we haven't gotten out of the program yet, that means no return statement was issued. Right, that means the element hasn't been found yet. It can still be present. Right, so next what do we need to check?
If either of the begin or end is equal to the K.
Correct. So let me just write, if it is equal to 1, that is the difference between end and begin. If it is equal to 1, then there is exactly 2 elements that we need to check, right? So the if condition will be what? If L of begin is equal to K, or L of end is equal to K. If any of this is true, then return 1, else return 0. Now have we covered everything in binary search? Is anything left? All the conditions are
Ma'am, this
checked or not?
this if condition has to come out of the while loop, no?
Sorry. This will be outside the while loop, correct? Yeah. So now this is okay. We have checked all conditions, whether it is present in the list, whether it is in the beginning or the end. If none of this gives us a match, that means it is not in the list. Okay, so this is the code for binary search. Now let's try it once. Just a second. So give me a list, give me any 6 elements in sorted order. Okay, let's just take 10, 20, 30, 40, 50, 60. Print binary search list, and what element do I want to find? Let's say I want to find 50. Okay, if I run this, 50 is present. So that's why it is giving 1. Yeah, at the end it is giving 1. There is also this print statement. No? That's why the 0 is coming. Let's remove this and this also. Yeah. Now if I run, see, 50 is present in our given list, so it is 1. Okay, now if you can use that code that I showed you for the time method, so what you can do is just write in a variable, take the time before you run this print statement in line 36, and take the time after you run this print statement, and then find b minus a. There is a time difference. So check this for linear and binary. You will see that there is a huge difference. Okay, if linear search takes some some 2 point some seconds, binary search can do it in 0.02 seconds, something like that. Okay, so is normal binary search clear with iteration, everybody?
Yes, ma'am.
So now we will do in recursive way. Okay, this is the last part of this week, so last code we will do. Binary search.
In the binary search, when we have a even number, length is even, there will be a both the left hand side or the right hand side will not be symmetric. Is that correct?
No, not be symmetric. Yes.
Yeah, but it will be symmetric when the length
when
is
the
odd.
Number of elements is odd. Yes.
Okay, right. Thank you.
Okay. Now let's write a new procedure called recursive binary. Okay. I'm going to create a new file. So what do you think will change from the before procedure that you saw using iteration? In recursion, what is the thing that needs to be repeated? Any idea? Okay, fine. Let's see. While we write, we will see. Okay. So definition, wait. So definition, let's call it recursive. So I'll call it R binary search. Now the arguments will change a little here. Okay. So the first thing is we will take the list. Okay. We will take the element we want to find. We will also take the end and the begin from here only. Okay. I'll explain everything once it is written. So this is recursively to compute binary search in a recursive manner. So first I'll write comments for everything here. So let's write if begin and end are the same, then what do we do? If begin and end are same, then we can just check any of the indices for the element we are looking for. Then we just check. Let's say I'll just check L of begin, since they are both the same index. So first condition will be if, see, now since we are writing a recursive way, so we have to make sure that the base conditions come first, right? So if begin is equal to end, if the indices are both at the same point in the list, then next you will check if L of begin, you can also check for L of end, okay, since both are same, is equal to what you are looking for, k. If so, simply return 1. Else return 0. Okay, so this is base case. Now if, okay, next what we will check, if begin and end are consecutive, that means begin end minus begin is 1, the difference between them is 1, that is their consecutive indices, right? Earlier we handled all these cases at the end, now these are our base cases, so we are handling them at the beginning. Okay, so first thing is if begin and end are consecutive, then check them both individually. So next statement will be what? If end minus begin is equal to 1, then first we will check both of them in the same statement only. If L of begin is equal to k, or L of end, sorry, L of end is equal to k. If any of this is true, then again return 1, there is element found, else return 0. Okay, so all these cases are now handled. Next, what is left now? Now we will check for those cases where end minus begin is greater than 1, which was our previous while loop condition, right? Where end minus beginning is greater than 1. So next you will write, okay, let's comment this also. If end minus begin is greater than 1, then what we will do? Just write if n minus begin greater than 1.
Excuse me, ma'am.
Yeah.
Ma'am, in the 10th line, you wrote to check them both individually. But in the 12th line, you write odd statement.
Yeah, individually
You
means
should
check.
write
No. Individually means what? That check both the indices. So I can write it using a single odd statement also, that if either of these are true, then return 1. Okay, individually means check both indices, begin and end.
Okay, ma'am.
Okay. So if n minus begin is greater than 1, then what we were doing? Now we have to find mid, right? That means there are more than one elements between end and begin. So find mid. So mid will be what? What is mid? Tell me, anyone.
End minus begin by 2.
Plus
Will you do minus?
end
End
plus begin by
end by 2. End by
It is begin plus
begin.
end by 2. Simple. Just take the first index, last index, sum them, divide by 2. Just in any case, if you want to just find the middle element in any list, this is the way, right? First index plus last index by 2. Okay. Next, what do we do? Now we will check for all the cases. So if L of mid, first let's check for greater. If L of mid is greater than k, that means k lies in which half, first half or second half? If k is smaller than mid.
First half.
Mid
So
minus
which
1.
will be updated, end
First
or
half.
beginning?
Will be updated.
End will be updated. So end equals to mid minus
Mid minus
1.
1.
Mid minus 1.
Okay, next condition what we have to check is if L of mid is less than k,
Is lesser than k.
then what will change?
begin equals to mid plus 1.
Begin equals to mid plus 1. That is second half of the list I have to check now. Okay. So now what is left? What is left? After this is done, one more case can be that the middle element is the k that I'm looking for. So if
Yeah.
L of mid is equal to k, then return 1. Right.
But this
Now,
condition could be the first condition, right now in the sequence.
yeah,
I know it
any
doesn't
sequence
matter.
works.
Yeah. Okay.
Better you write this in the first condition. Yeah, that is better. It will save time if the middle is k.
Yeah.
Right. So if now all the conditions are checked, now what is left? One more condition. What if end minus beginning becomes less than 0? When will it become less than 0? When we have actually gone through every element in the list, right? And now begin has shifted to a position which is greater than end. That is, let's say end is now at 4th index, begin is now at 5th index. Because you have been shifting, let's say you are shifting the begin index, that is every time you are checking for k, it is some value which is less than the mid. So you keep on shifting begin to mid plus 1. Like this, at one stage you will reach such a point where begin is greater than end. Right? Whenever we reach such a point where end minus begin becomes less than 0, then
How
we know
can
that
it come? Because begin is always towards the left side, right? It cannot exceed the end, right?
but you are
Can,
doing what? See, at one point, since we are
can
continuously,
you, yeah,
yeah, yeah.
if you can take an example and I think a small list.
See, so if I try to check in this list 1, 2, 3, 4, 5, and I'm trying to check, let's say, some element that is -2, if it is present in this list or not, right?
Okay.
So first what will happen? Begin is here, end is here. This is index 0, this is index 4.
Correct.
First find the mid. So mid becomes what? 2. 0 plus 4 by 2. The second index is at 3. So this is now our mid. So we have to check, is mid greater than my k? This is my
No,
k,
it's
negative
false.
of 2.
False. Yeah.
No, mid is greater, right? K is
Yeah, yeah.
-2, so mid is greater. So now I will change what? End. End will be shifted to mid -1 because definitely I think that k lies in the left part.
Yeah.
So end is equal to mid -1, mid is 2. So end is 1.
1.
Okay. So this is my end index.
So L is equal to 0, end equal to 1.
Yes. So now if I try to find the mid here, so 0 plus 1.
0 plus, yeah, 0
Okay,
plus 1 by 2.
this is actually that first thing that we checked, right? That if end minus begin is 1.
Correct.
Okay, so end minus begin 1. In that case, what we did, we have to check
Just check
both of these.
both conditions.
Right. So we check both of these. None of this is matching with -2. So we go to 0.
Yeah.
Okay. But in some case, it can happen that your begin exceeds your end. That means your begin goes to some place this, while your end is still here.
Okay.
That is, end comes to the left side and begin goes to the right side because you keep on increasing the mid. That is, you keep on shifting begin to the right, but end is staying the same. Okay, in some case it might happen. That means, see, whenever the case is such that what was our in iterative process, the while condition was what? End minus begin greater than 1. So what are the other two conditions? That end minus begin can be equal to 1 or it can be less than 1. So whenever the time comes when it is less than 1, that means that there is no possibility to find it. That means the element doesn't exist. If this is true, that end minus begin has become less than 0. In that case, the possibility is that you have to return 0 because the element is not found. You have traversed the entire list. That's why begin moved to a greater index than end. Okay, so this is also one condition we have to add. So if I put it here, then it will be outside of the if, this if. loop. So here you will just write if end minus begin is somehow less than 0, that is begin has reached some greater index than end. In that case, you can directly return 0. So there are actually 3 different cases in which there is a possibility to return 1, that yes, the element is still present that we are looking for. First possibility is when begin and end are both equal, both are at the same index. In that case, we will just directly check any of the indices because both are pointing to same index. If it is present, okay, return 1, otherwise return 0. Second case is if end minus beginning is exactly equal to 1, that is end and beginning are at consecutive indices. In that case, you have to check individually both the indices if anywhere k is present. And third case is the biggest case, that is when end minus beginning is greater than 1. That is you have more than one element between end and begin. So at that point, you have to keep on finding the mid and updating begin and end until you reach k. And after doing this also, if you can't find k, then you will reach such a point where begin has exceeded end. That is end minus begin is now some negative value. Okay. In that case, directly return 0, so there is no more scope of finding the element. This is the recursive way. Okay, is it clear? So see, if I want to write, okay, here one more statement you have to write is return R. This is the main statement I forgot to write. This is the recursive call. R binary search L, K, begin, end. Right, after you update the begin and end here, you have to call the next call with the new begin and end, right? So here you will write the return statement. Okay. Now let's try it with a list. Let's take a list L, 10, same list I'm taking 10, 20, 30, 40, 50, 60. Just print R binary search. So what is the list is L, element I'm looking for, let's say 50. What is the first index? 0. Last index is always what? If you don't know what the list is, how long the list is, just simply write length of L minus 1. Okay, now if I run this, okay, something is okay. So this is a small L. What is giving an error? Function object is not subscriptable. Okay. So you have to add the parenthesis here, no? Now it should work. Missing 3 positional arguments, k, begin and end. How is it missing? I've given the arguments. List is there. Wait. Okay. So 50 is present in my list, so it is giving 1. And if I give here minus 2, this should give 0. Right? So it's giving 0. Is this code clear, everyone? Recursive way. Any doubt? Not just this, I'm also asking the iterative way, the recursive way, everything we have done. Any doubt in anything? This will take some time. Okay, you practice this code at home, write it on your own. Linear search is very easy. That doesn't take much time. Binary search is a bit difficult because there are so many cases that can happen. Right, but the main idea is that you have to keep on halving the list every iteration or every recursive call. Okay.
Excuse me, ma'am.
Yeah.
Ma'am, please explain print line.
Which one? Oh, this is
Last
just
one.
this is just I'm checking whether the code is working. So I'm calling the function, right? R binary search, recursive binary search. What are the parameters? First you pass the list, then you pass the element you are looking for, Then you pass the first element, begin index. That is zeroth index is always the begin index. And end index is what? Last index, that is length of L minus 1. Length of the list minus 1. That is the last index. Okay.
Okay,
So
ma'am.
if this second this k is present in a list, it will return 1, otherwise 0. Okay.
Ma'am,
So
for the
if it,
same yeah, go ahead. Sorry.
no, you continue.
Uh, for the same R binary search, if we don't give the start and end and only give a list and the value to be found, like similarly what you have shown for the linear binary search in without recursion.
This yeah, where
Yeah,
did that
in
go?
that
This
we
one.
just gave the list and the value to be searched. How it is? Why we are giving in R
Yeah,
search?
here also this is possible. Okay, I did it because the prof did it in this way. Here also you
Okay.
can put that. Okay, you can give the direct index, begin and end. I don't think there shouldn't be any difference. I mean,
Yeah.
you are saying that why I'm passing it as parameter, right?
Yeah. Okay, we can
Yeah,
even find the begin and end
yeah, sure.
inside the function, right?
Because list is being passed, so you already can find length of L minus 1.
Yeah,
So you can do it inside the function also, no problem.
Fine. Okay.
Okay. So if anyone has any doubts, you can definitely ask in the next session also, because the concept is all covered for week 9. Now I'll just do the practice problems and everything. Okay.
The challenge here, ma'am.
Ma'am, when will
Just
the
a
revision
question.
session?
Revision session for
Quiz 2.
quiz 2. Okay, I'm not sure. I have to check. Okay, I'll check with the team and let you know.
Quiz is not there, no, for Python.
No, quiz 2. I'm sorry,
I think
OPE2. I thought you said.
Yeah,
Quiz 2 is
OP2,
not
not
there
quiz
for
2.
Python. Yeah. OPE2 is later on. I think it's at
Yeah.
the.
After the quiz 2 date, OP2 will come.
So before that, we will definitely have a revision session.
Ma'am, hello?
Yeah.
Hello? Are you listening, ma'am?
Your voice is not clear. Can you speak a little louder?
Can you hear me now? Can you hear me now? Hello?
Yeah.
With regard to the OPP exercise that they have released, what I see is that in some cases the deadline is given as March 16th. In other cases, it's been given as April 3rd.
Yeah, I also saw that. I am also not sure why that is coming. I think it's some glitch or something, because it is all under the same exercise.
But earlier also, last time also, we had the same issue that
Right.
dates were different. And this time also we are facing the same issue. And even in the exercise also, I think I also mentioned to you last week about in the exercise also we had the situation.
I told this to Livin already. I think he will update these also. So, okay, I'll tell him today also once. The exercise problems for OPE2, right? Those the dates are not coming same.
The Jan 25. And with
What is
regard to
what is the
OPP,
earlier one? What is the earlier date?
the
16
the
March.
first date was 16th of March, and that is it's a kind of mix. Some of the exercises are 16th of March, the rest of them are in April 5th.
Okay. No, it should not be May. Definitely, it should be in March only.
Yeah. And second part, we are on OPP1, the OPP2 exercise that were given that time. I thought those exercises will also be extended for the further deadline, but not extended is still.
Yeah, that is not. I don't think it is getting extended. I don't think it's getting extended. Because I also asked about it, I didn't get any response. I don't think they can extend it. So the exercises that are available now, those you can solve.
But are these exercises I didn't do I don't know about others. So are we going to get graded for this exercise?
No, not graded. Just for practice, these are. The graded ones are mentioned. Okay, just the ones that are mentioned, those are graded.
Okay.
Hello.
Thank you so
Hello.
much.
But still, I will ask about this deadline and let you know. Yeah.
Please. Thank you.
Hello.
Yes.
When the OPP1 result out, ma'am?
Result, I have no idea. These things, these are up to the support, right? I don't know about the results. But they should be out in a week, I guess. This week only, I think they should be out.
It's already released. It's already released.
Yeah, the solutions are given to you, right?
Yeah, even they have released the result also.
Okay. Then you should be able to check it on your portal.
They have sent a mail. They have sent a mail with a different times
Just
schedule. I think all of us received that. So we need to. But only thing is a kind of roundabout. And I think somebody, one of the TAs told that it will be updated in the dashboard sometime in the coming
that's
days.
what I'm saying. In the dashboard, it will be uploaded. Yes, for everyone that should be visible.
But if we follow the link, I think there we can see the scores there.
Yeah, if you have gotten a mail, just check the link once. Otherwise, anyways, it will be uploaded on the dashboard in a few days. Okay.
Ma'am, one
Okay.
question. With respect to
Yeah.
the recursion, given a problem, is there any tips you can give so that we can arrive at the
See, recursion when you want to apply, right?
Hmm.
So any problem that can be solved by recursion can also be solved by iteration. Recursion is just the faster method. But only right recursion.
Yeah, that part I understand. My question is when we want to, when a question is given in exam and said that we need to solve this through recursion, is there a structured way to arrive at that endpoint?
Yes, see, the first thing you have to do is when you are writing the function, right, that is going to call itself. The first thing you write is the base case. Like for factorial, it's the 1 factorial. For compound interest, is the first year interest. Anything. I mean, base case is always what will trace back to the last call. That is your base case. Okay. That thing you'll write first. Next, you write the condition for the recursion. Like in the simpler problems, it is just a one line condition, just the return statement is a recursive statement. In more complex problems like this binary search, you have to write all these cases like I wrote here, and at the end you can again call the binary recursive call. But the structure is mainly this: first you go for the base case and check that if it is already satisfying whatever you're trying to do, then you return one there only. Otherwise you go to the else part. Else part will have the recursive call. Okay, but these things will take some time to, I mean, write on your own if this is the first time you're doing this. So just do practice more problems. Okay, I can give you a problem sheet next class. I have recursive problems on recursion. I'll give you a problem sheet.
Okay, but the OPP2 will also be covering this recursion.
Yes, it will cover.
Okay.
Okay. All right, then please join the next class. There the problems will be discussed, practice, and other graded practice assignment also. Okay. Yeah. Thanks for joining, everyone. Thank you. Good night.
Bye.
Thank you.
Thank you, ma'am.
Yeah, and these codes
Good
I
night,
can
ma'am.
share with you. Okay, I'll share the code in the next class. I'll give you the drive link.